Okay, so my talk is about crossing over and keyframe learning. I'm Hangyu from Tufts. Keyframe demonstration, unlike the trajectory demonstration, the keyframe demonstration is a sparse set of constructive poles or keyframes. One core problem of using keyframe demonstrations is we lost the trajectory information between the keyframes while acquiring accurate pulse information. And we're inspired to fill the keyframes and genes and use genetic algorithm to generate more keyframe sequence, since we need to fill the gaps between the keyframes anyway. And we proposed our learning framework. First, we collect keyframe demonstrations using kinesthetic teaching. Then we use the dynamic time wrapping to clustering keyframes. And based on cluster keyframes, we perform the crossing over to generate more keyframe demonstrations by swapping the keyframes in the same cluster, but from two different demonstrations. And also we used this step is called crossing over. We did not involve the mutation yet. And then we replay all the keyframe demonstrations, include generate demonstrations, and ask participants to evaluate all the replays, and performing learning based on evaluated replays. The learning algorithm can either be reward learning or a reinforcement learning. Okay, that's it. Thank you. If you have any questions, please reach me at the post session or email me. Thank you.
Thank you very much. Our next lightning talk would be on learning goal recognition models using human examples.
Hi, yeah, this is my talk. It's a work with Leo, Rosa, Amado, and Felipe Meneguzzi. What we have been doing in our work, basically, we come from the goal and plan recognition community, where our aim is to try and understand the goal of an agent, usually a collaborator that we want to work with. So traditionally, if you see on the top left, in goal recognition, the way that traditional goal recognition works is that a domain theory is hand-coded. This is usually PDDL, HTNs, grammars, and you get some raw data which you parse using activity recognition, and then you use some algorithm, parser, planner, to understand, given the recipes that you got and the data that you got that was tokenized, what the person is doing. What we tried to do, and we published a paper on that in AAAI just 2 weeks ago, we replaced this domain theory with a learned domain theory, which is based on RL domains, on MDPs, where each goal that the agent can try to accomplish is basically now represented using a policy or a value function of what the agent can try to do. So we have policies that are goal dependent. And now when we get an observation, we use measures, specific measures that we developed to do the goal recognition process. So now that we have this tool and we have goal recognition that is based on reinforcement learning, we can leverage that to, instead of learn this from reinforcement learning processes, learn this model from human examples. And this is why we were interested in presenting this in this workshop, because I think that the people here will be the best people to give us feedback on what exactly and how exactly to do that. So this is more of a future work and the next step that we want to do, but I'll be happy to talk to everyone who wants to talk more and see how we can extend that. Thank you.
Great, thanks, Reuth. Our next talk is interactive robot task learning, human teaching proficiency with different feedback approaches.
Okay, I'll share my screen. Okay, I think you should see it now. My PowerPoint is really slow today, so I hope that works. So I'm Anna, I'm with Bielefeld University, and here's some work we have done on humans teaching robots with different feedback approaches. Our system, So now our system ran on a Pepper robot, a SoftBank, and it should learn the movement skill cup and ball. So we used an imitation learning approach, as you can see here in the video. We gave the robot one demonstration via kinesthetic teaching. And the movement, that is the sequence of joint angles, was represented with a radial basis function network, so we had much less dimensions, and the movement was then optimized using simple black box optimization. Usually, a camera setup is used to determine the cost for each rollout according to a cost function defined by an expert. In our work, instead of a cost function, in a camera setup, a non-expert user is providing rewards via a simple user interface. So what we did is we conducted a user study comparing absolute scale feedback and preference-based feedback. And in the absolute scale condition, the user gives a 1 to 5 star rating for each rollout, as you can see here in the picture on the left. And in the preference-based condition, the user could choose which one of 2 presented movements was better on the right. We wanted to find out what feedback type works better in terms of user experience and system performance. 30 non-experts participated in our study, and we found that there were no significant differences for the subjective user experience between the conditions, but there was a significant difference in learning performance. So the preference-based system learned the task quicker. And for more details, please come see my poster.
Thank you very much. Our next talk is human ocular data for robot learning feedback.
Okay, let me just get my video started. All right, cool. Hello, my name is Christina Petlowany. I am at the University of Texas at Austin, doing research with Dr. Justin Hart and Dr. Mitch Pryor. We're talking about using sending gaze data to robots in order to help communicate and help train them while they're performing tasks. So gaze is just a really, is a communication modality. It can indicate a lot of things about a human user. And the existing studies use it mostly for training before the robot enters or starts performing, or afterwards to grade robot performance based off of how people look at the performance. And the creation of this augmented robot environment really sets us up in order to send real-time gaze data to the robot. So Augury is an augmented reality HoloLens 2 application to display robot info. And it provides a method for a low latency communication between an augmented reality headset, the HoloLens 2, and the robots. The HoloLens 2 also has some innate eye tracking capabilities. The experimental study plan here, so this is proposed research, not research that has been undertaken yet, that we're hoping to get some feedback on, is to record gaze data to create models of what this gaze data looks like when the robot is performing its task incorrectly, and also when it's performing a critical level of fault. So if it's about to do something dangerous, for instance. We expect kind of some longer visual attention on the robot when it's doing something incorrectly, as people are questioning what it's doing. But also if the human has a secondary task, say an assembly task that they're working on while the robot is performing its own task, that when the robot is about to do something dangerous, that they're going to switch their attention from one task to the other faster. And then afterwards include this in the robot model with the robot training, and to do a study whether with these different fault levels and the different gaze data. The main learning task is going to again be on this performance of the task and this gaze data, that the robot is maintaining good performance. So for an inspection task, that the inspected object would be in the field of view. It's a safe distance from the object, and then how these gaze cues can be used to inform robot behavior. And we're really excited about Augury and it's setting up for this type of research. And we're excited to see if it does really enable this type of capability. All right, thank you.
Okay, fantastic, thanks. Our next talk is based on the paper Revisiting Human Robot Teaching and Learning Through the Lens of Human Concept Learning Theory.
Cool. Okay, I made a pre-recorded thing to keep it short. So I will share that. Hopefully you all can see. And then
I'm Serena Booth, and I'm introducing our HRI paper on revisiting human-robot teaching and learning through the lens of human concept learning. In HRI, we often focus on modeling the human's behaviors from the robot's perspective, but the human's conceptual model of the robot's behaviors is equally important. We consult cognitive theories of human concept learning to inform how we should design interactions to support the human's conceptual model formation. Analogical transfer theory asserts that analogy, or finding and using relational commonalities, is a building block of human concept learning. For people to benefit most from analogical transfer, we should align familiar base context with unfamiliar target context. Through this process of structural alignment, people are readily able to transfer their knowledge from the familiar to the unfamiliar. Analogical transfer provides an explanation for why more human-like motion, like you see on the left, is easier for people to build conceptual models of than less human-like motion, where the robot first moves its wrist joint, then its elbow, then its shoulder, like you see on the right. The variation theory of learning explains how people use variation to distill core knowledge from superficial details. For people to benefit most from variation, they should first experience contrast, where the critical components of a concept vary, and only later should they experience generalization in the form of varied superficial details. If our goal is to help a person learn a conceptual model of a robot's policy, the person should first experience what that policy is not by seeing alternative policies. Only after this should the person experience the policy being held constant, while other details, such as the configuration of the environment, change. To assess how human concept learning is or can be used in human-robot teaching and learning contexts, we conduct an extensive literature review. We put together a website as a living resource. This website lists all of the papers we reviewed alongside our analysis of their use of human concept learning principles.
all right, thanks.
Thank you. Our next talk is, correct me if I'm wrong, using non-experts to repair reinforcement learning policies.
All right. All right. Yes, so I'll be presenting our work on using non-experts feedback to correct robot policies after failure. When we deploy learning-based robots in the real world, at some point they will fail. For example, if an object is no longer available, or if an action that was previously successful suddenly lead to an undesirable outcome, for example. And in many of such failure cases, the robot needs additional rules to correct the failure, and those rules can actually be provided by non-experts, so people with not necessarily programming or robotics experience. Our research is motivated by the question, how can we automatically correct robot failure on the fly using non-expert feedback? Prior work has looked into learning from human input and enforcing desired robot behaviors, and our work is different as we query non-experts, and we query non-experts only after the failure rather than throughout the whole training process. And we apply shielding to correct policies after deployment rather than during training. The robot is trained as a reinforcement learning system and is deployed in a different environment. Upon failure, it queries a non-expert to ask for feedback, and that feedback is then used to generate a shield to correct the robot's policy. And we retrain the system with this shield. So this way, robots do not need to fully rely on experts to correct their failures, and we can formally verify the corrected behaviors. We constructed shields to correct high-level actions in a common daily task, a cooking task in this case, in a 2D kitchen environment. And we used ground truth and incorrect feedback that we obtained in an online study. We tested 3 types of shields. Action refinement, which refines a failed action by executing another action or a sequence of actions instead. Alternative item, which replaces a missing item with an alternative item. And forbidden action, which removes undesired actions. Results of our 3 simulated experiments showed that shielding always successfully learns the task in contrast to using no shielding. And it's more data efficient than using no shields even when we add additional expert knowledge or do reward engineering. And incorrect shields resulted in infinite loops of corrections and non-generalizable solutions. This work is a proof of concept. We have not yet automated the shield synthesis and not yet tested on the real robot, so open questions remain about what information does the robot need to provide to the non-experts in order for them to effectively help recover after failure. And how can we abstract low-level control actions to higher-level actions that are interpretable for non-experts? And thirdly, also, how suitable are spatial temporal logics with which we can create formal specifications so that they're understandable, intuitive for non-experts to use. So to come back to the overall research question that I posed in the beginning, what this work showed is that combining non-expert feedback and shielding has potential for automatic verifiable failure correction. Thanks, and you can find the paper here and reach out if you have questions.
Thank you very much. Our next talk is CoFrame, a system for training novice Cobot programmers.
Can everyone hear me all right? Yes, I think. Okay. Hi, everyone. I'm Andrew Schoen. I'm presenting the work on CoFrame, a system for training novice Cobot programmers, which is a joint training programming interface for teaching novice programmers how to construct collaborative robot programs in manufacturing contexts. All right. So this aims to actually solve this kind of growing skills gap that's in the manufacturing setting, where the people that are actually put in charge of programming these robots really don't have the skills that they need in order to actually do this. So we created a new system that attempts to provide this feedback in line with what an expert mentor might actually provide. And this is heavily based off of an expert model that was developed by Siebert Evanstone and colleagues. It used a method called epistemic network analysis, and they looked at experts to kind of see their discourse while they were programming, while they were discussing about how they program cobots. From this model, we actually constructed 4 higher level interconnected expert frames that are meant to provide feedback to these novices. The frames are safety concerns, program quality, robot performance, and business objectives. Each of these different frames had a different set of issues that they can provide as feedback for those novices, and they can actually have dependencies on one another. So for example, reachability of a pose is only really, it's something that is addressed before you would consider whether or not that pose meets certain safety criteria. So we integrated all these issues into a new system called CoFrame, which you can see here. It features a review section on the left, a simulation and info section in the middle, and then a visual programming tool on the right. The key feature of the system is, again, those issues, that feedback process. And so a lot of that feedback is visual in the simulation. So we have a bunch of different issues here. This is just a subset of them, but it includes unsafe gripper movement, pinch points, occupancy, missing parameters in their program, reachability, joint and end effector speed, space usage, and cycle time. And so these issues are tracked during development with as they make those changes in the visual programming language. And then those visualizations allow them to kind of better see where those violations occur and revise their program. So for more details on the system, I encourage you to check out our paper, and thanks.
Thank you very much. And now to our last lightning talk, learning socially appropriate robo-waiter behaviors through real-time user feedback.
Sorry, I hope you can see my screen.
Yeah, we can see.
Can you all?
Couldn't hear you.
Okay, good. Okay, great. It's not getting feedback. I was like, what's happening? Great. So I'm Nikhil. I'll be talking about our paper on learning socially appropriate robot behaviors through real-time user feedback. So humanoid service robots need to learn behaviors that are consistent with what is considered socially appropriate by humans. This could be learning approach behaviors when there's a group setting, or if it's a complex home environment that needs to learn how to approach everything in the environment, or even facilitate humans in restaurant settings, for example, for robo-waiters. So we particularly focus in this work on Pepper as a robo-waiter learning approach and position behaviors, for which we simulate sort of a grid world scenario for our restaurant settings where the customer table is right at the center, and the robot needs to figure out how to approach the table to take the order or to talk to the customer. So one question that arises is that how do you establish what is considered socially appropriate? So we use a crowdsourcing approach to gather appropriateness ratings, where we basically create images of the robot being in different positions across the table and ask people to annotate how they felt about it, either in terms of how appropriate they felt the robot positioning was, and also what they felt in terms of arousal and valence about robot being in that position serving them. We also created GIFs for the robot moving in position to also gather data on appropriateness of speed. So I'll talk about position heads, what it looks like. From 1 to 5, we see that positions in front of the table, nearer to the table, are considered more appropriate, while behind the table positions are generally considered inappropriate by people. So we use this data, particularly top right quadrant, pie, you'll read in our paper, to basically form a reinforcement learning problem around it, where we use these position ratings to map the reward function for the robot. In the offline settings, we compare 3 different reinforcement learning models to see how they perform with this data. And we see in our case, particularly DQN performs the best and is the most stable. So we use this DQN model then to see how if we can adapt with people in terms of their individual preferences and how they would prefer the robot to be. So we conduct an HRI study with 21 people where the robot has 4 tasks, basically welcoming people to the diner, taking their order, coming back with the order, and also collecting the dishes later on. As this was during peak COVID settings, so most of this was sort of acted out and not actually done with dishes and food, but there was still a participant and the robot that were interacting with each other. So we basically have a within subject study where the person interacts with the robot across 4 settings. Firstly, a randomly positioning robot that positions itself randomly. Then we use the pre-trained DQN model on the crowdsourced data. Then we add explicit feedback as adaptation method on that pre-trained learning model, where we use this sort of keyword spotting to map reward function. And we use implicit feedback as another criteria, particularly looking at facial valence and using that as an additional feedback. So the reward function was modified to include both the crowdsourced rating as well as the implicit or explicit feedback based on that condition. So to evaluate how these conditions compare, we look at 4 different criteria. Firstly, enjoyment ratings, where we see the adaptive conditions, which are explicit and implicit feedback conditions, generally perform much better than non-adaptive or pre-trained conditions. They're less tiresome, they're more impressive, satisfying, and so on. For sociability ratings, we see the explicit condition is more sociable, obviously, because the person is talking to the robot all the time. It's also considered more human-like. For adaptability, we see similar trends where explicit and implicit condition is where the people felt that the robot understood what they said and adapted to what they wanted the robot to do. Implicit condition also was rated the highest in terms of understanding how they felt, which was sort of the motive behind it. And finally, for appropriateness ratings, again, we see that explicit and implicit feedback conditions are considered much more appropriate in terms of robot positioning and speed of the robot. So we present sort of the first work in investigating real-time adaptations for HSRs in particular. We show that crowdsourcing appropriateness ratings to get a generalized idea of what is considered appropriate actually works. And using that data and then building on it using explicit or implicit feedback actually improves people's interaction with the robot. Thank you so much.